Okay, welcome back. And let me just 1, 2, 3, 4, 5, 6. Well, less than half. Okay. Okay. Let's go quickly recap where we were the last time. We'll try to end class a little bit earlier today. We'll see if we can finish everything we want to finish. If you remember, we were working on a completely numbers-free discussion the last time. We were talking about the best strategy that will get you from, I think it was home plate to second base or what, as fast as possible. There are two proposals. You either run narrow angle or wide, right? So you're basically comparing them. And you all did a very good job answering these things. I just want to very quickly recap. There were three studies you could do, all in different levels of quality. The worst study you could do is an observational study, which is basically do nothing, go to games or watch videos and time how long it took people to run that particular way, how long it took them to get from point A to point B, basically. So that's the worst quality study because you basically cannot make any causation. It's a very poor design, but it is something, all right? It's better than nothing. The other design was you have 20 players and you are going to do it as an experiment. You randomly assign some players to run narrow, some to run wide. The key point is everyone only runs one angle. Some run narrow, some run wide. You just record the time. What's the issue with this one? People run at different speeds. So it could be that everyone that was told to run narrow also was a fast runner, something like that. Now, I want you to realize that the second design, the one with the 20 baseball players, some run narrow, some run wide, that is a classic chapter 6 kind of data set. You have two buckets. You are the narrow angle bucket, you are the wide angle bucket, and you only do the one thing. One group doesn't even need to know about the other group. That's chapter 6, and you should have finished your homework based on that one. Then there was a third proposal where you still have your 20 players. The same 20 players is how you use them. Now you make everyone run both ways. You make everyone run both ways. And once everyone runs both ways, that takes care of the issue of the different speed at which people run. Why? Because you're running against yourself. Who's a better control than you? No one. You do both things. And this kind of study is called a repeated measures design. That's study design number 3. Now, then we ended the class last time by showing you a video where how do people choose teams in physical and in PE, right? They basically have in their mind, they have a list of who's the fastest, who's best, who's next best. And so the team captains start calling, okay, that was the purpose of showing you the YouTube video that, okay, you come, I want you. It's a sorting of people by ability. Now, with that idea, I want you to think about a fourth study. You still have the 20 players, but now you have some additional information about them. You know how long it takes each player to do a 100-yard dash. So you know how fast they run, basically. How could you use this information to create pairs of runners? So I will ask you to do this online. Let's say here are the players listed by decreasing speed. Okay, so let's say player 19 is the fastest runner. The next one is player 6. The next one is player 3. The next one is player 14. I think you get the idea. Okay, so 19 is the fastest runner, 6 is the next fastest, and so on. Can anyone tell me, with this information, how would you pair them up to do narrow angle, wide angle? Anyone? You already have a list of players by their speed of running. What would be a smart way to pair these people up so that someone only runs one way and the other person in the pair runs another way? Anyone have any idea? What would you do? That's right. Wouldn't you pair up these two? And then wouldn't you pair up these two? So you would do this. Thank you. So you would say P19 and P6 form a pair. Then P3 and P14 form another pair. These pairs are called matched pairs. I hope it's for obvious reasons. You have matched them on their speed. Then, within each pair, you assign one person to run narrow and the other wide. This assignment should be done, and what's the one word I want? Randomly. Good. So, do you see in essence, thank you, do you see in essence that the four designs are totally different? The first one is observational. Watch videos. Take a timer. Second design is an experiment. You randomly assign people to run narrow, wide, but everyone just runs one end. The third design, everyone runs both. And that's called repeated measures. The fourth design is everyone runs one. But you pair people up so that they are as similar as possible and then have one person run one and run the other. Do you see the difference between the four designs? All right, so there are four. So let me now ask you this question. Of the four designs, which I've just told you about, which one do you think is best for this context? There's no right or wrong answer here because every design can be justified. But if you had all the resources in the world, which one would you think is the best at answering this question? I have my views on this, but I want to hear your thoughts. Which design? Is it the okay, is it the observational study? I hope you don't say that, okay? Is it the observational study? Is it the independent groups? Everyone runs once and only once? Or is it the repeated measures? Or is it the matched pair? Which do you think is the best? Anyone? There's no right or wrong answer here. I want to know if you say that you say, okay, I think this design is the best. Can you tell me why? You don't have to type. You can tell me if you want. Right? What do you think? Yes, good. I like that. Three or four. I think no one's going to say one or two because those are clearly not so good. So let's phrase it this way. If you say three, can you tell me why three is better than four? If you say four, can you tell me why four is better than three? All right, can you do that? Because in other words, there's no right answer. Both are okay. Three, okay, I'll put what three is. Repeated measures is better than four matched pair. Matched. Oh, there's, yeah, matched pairs because, can you tell me the because? And then we will also give you a chance to say four is better than three. Because of what? In other words, actually, you can make an argument either side. All right, think about it. I'll give you some time. What do you think? How would you justify to someone why you say repeated measures is better in this baseball problem? And then, conversely, if you are a proponent for matched pairs, can you tell me why you think it's better than repeated measures? You can give me any reason you can think of. I'm hoping you can come up with these things on your own so you can justify them. Good. Three or four is clearly superior to one or two. I agree. All right. But can you justify why you say three is better than four? Any ideas? Anyone? Very good. That's exact. In other words, just because they were ranked by speed, there could be a disparity. Yes, there could be a jump. And so I'll phrase it this way: no one can be a better control for you than you. Repeated measures is the best if you're talking about controlling everything. Who's more like you than you? No one. Right? If you go Google, I think there's an old song called I Am My Own Grandpa or something. You can go check it out. It's something like that. You're your own grandpa. You are your own control. Who's more similar to you than you? No one. See? Now, but this one is, I think, slightly more interesting. What if you couldn't do repeated measures for some reason and you had to use match pairs? How would you justify? How would you how would you sell the match pair method? Think outside the box a little bit. What could be good about match pair? I know this in this. I would say my personal answer is 3 is the best in this context. But can you dream up a reason why you would say, no, let's do it as a match pair? Can you think of any reason? It's a bit out of the box, this one. If you can't get it, I'll tell you. But if you can dream up something that would justify, I always have great confidence in the class because students really can think outside the box. So I would like to know what you think. If you had to sell the match pair design, and this is going to be linked to 7, can you dream up a situation outside baseball, some other context, where even if you wanted to, you couldn't do a repeated measures design? Can you think of some other study? All right, I would like you to think about this as well, because most of you are from a variation of a lot of departments. Think about your own discipline. Or is there something you can think of, an example of some context where even if you wanted to do repeated measures, you couldn't? Can you think of it? So we'll do six. We'll do this and this simultaneously. Can you justify in any way why the match pair could be better than the repeated measures in the baseball context? And then can you think of another context outside of baseball where even if you wanted to do repeated measures, you actually couldn't? This baseball study you can. But can you think of a study at some other thing that you cannot do as a repeated measures? Anyone? Yes, exactly. Not everything in life can be repeated. Let me give you a specific. Yes, very good. So this baseball one, anyone? Clearly, you can do either design 3 or 4, but can you dream up something? I just don't want to give the game away. I just want to think, see if you can think outside the box. How would you sell the need to do a match pair in the baseball study? Anyone? Okay, well, I'll tell you, right? One thing I can dream up is it takes half the time to get the results. Do you agree? When you do a repeated measures, everyone has to spend the time to do it twice. Now, of course, running from one place to another on a baseball pitch is not, it's not, it doesn't take a lot of time. But what if you're doing a chemistry experiment and it takes 1 week for the reaction to be done? Wouldn't it take 2 weeks if everything has to be done twice? See? So time and money. Maybe it's expensive to do something twice. Maybe these baseball players, every time you make them run, they charge you $1 million or something like that. Then cost becomes an issue. Did you see that? So that's why I say think outside the box. It could be a time issue, a cost issue, and sometimes impossible. Let me give you a specific idea. Maybe that will help. In education research, let's say you want to know if one method of doing long division is better than another. You understand what I'm trying to say? So Remember the time when you first learned long division? Everyone learns long division. It's unavoidable. It is. I picked long division because it seems to be the point at which people decide that math is not for them. That seems to be universally agreed. I think people are fine all the way, but once long division comes in, people disengage for the rest of their lives. That's a very, very. It's one of those lines in the sand. I found. So that's why I picked this one. Okay, let's say you have two methods of teaching long division. So how can I compare them? Once I've taught you something, I can't unteach you. You see, I can't reverse the clock and clear your mind and then teach you method B. You can't do that. And therefore, in this kind of case, you have to do match test. If you want to compare how good a method is, maybe you teach something, then you give a test. You want to compare how good they are, you have to match your students. So, for example, if I wanted to compare teaching methods in a school, I would have to match students demographically, geographically, socioeconomically, so many things to think about. You need to make sure that students are as similar as possible because you cannot rewind clock. So as we said, something only works once. You cannot unteach someone. That is why you have to learn all the different methods that are out there, like that, the different designs. All right. So I hope this has been an eye-opening exploration. Actually, I mean, I always enjoy teaching this one because it gives students a chance to think about why is statistics important. You have to think about how you get your data and stuff like that. Okay, so we will now move to the chapter 7, which I want to talk about. Chapter 7 is exactly this kind of idea. I wanted to start with a kind of an abstract example first. We will start with an abstract baseball thing, but you see, chapter 7 is on when you are still comparing means, it's still means, but they come from the same person. Now, I want to point out this seems to indicate that this is only true for repeated measures. The good news is this: whether your data come from a matched pair or repeated measures, the statistical analysis is the same. In other words, the statistical analysis makes no distinction between whether something is design 3 or design 4. The data are treated the same. All right, so that's good news. So, but we're going to look at the repeated measures most of the time. Okay, so you're trying to compare the effect of two diets on the same person. You have a sample of adults. Two variables are measured on each adult response. First, you have the weight after 2 weeks of being on diet A. You're trying to compare diet A with diet B. Okay, you're trying to compare diet A with diet B. So obviously you record down two things. Now, how is this actually implemented? Well, it means that you have your people do diet A for 2 weeks, then you take their weight. Then you give them a resting period of maybe a month where they are free to eat whatever they want. Then you come back and do the other diet. And then I take your weight after 2 weeks. So that's actually how these kinds of things are done. There is a resting period so that you can go back to homeostasis, like whatever state you were in, then you do the other one. So that's what's going on. So you measure two weights on the same person. See, this is exactly baseball. You run narrow angle and also wide. Are these variables quantitative? I hope you say yes. These are weights. So yes. Anyone, what do you think is the explanatory variable in this study? What puts people into buckets? I know they do both diet. Yeah, that's right. Exactly. It is the type of diet that you're on, and clearly that is categorical. Notice we are recording weights after being on diets A and B on the same person. Same person. This is in stark contrast. And by the way, no one has asked me yet. The exam that's after spring break does not cover chapter 7. I'll send an email about this. That's just so you know. Chapter 7 is not finished yet, so it will not be on this coming up. It will be to 6. But I'll send an email about this. There's also going to be a review assignment. Just watch your email, okay? So notice that we are recording the weights of people after being on both diets on the same person. So chapter 6 is totally different. In chapter 6, you would have some people do A and some people do B. You don't do both. Two buckets. That's why homework needs to be done at the time where I assign it, because I want that to be very clear. What you have just, the homework that was just due was chapter 6, which is basically, didn't you have cars with manual transmission and automatic transmission? You can't have both. So chapter 6 is easy to understand. Some people do diet A, some people do diet B. They don't do both. Chapter 7 is different. You have everyone do both. So how is chapter 7 different? Well, in chapter 6, the diets will be tried on different people. That is, some people would be on diet A and some on diet B. This design that we propose is superior because everyone is his or her own control. Do you agree it's superior? Because those people have different metabolisms. So it's not the best design to have, maybe everyone that was put on diet A just happened to metabolize food faster or something like that. Then you would think diet A is very effective. So the whole point is people are highly variable. It is better to do it this way. So that's why you need to study chapter 7. And that is also why chapter 7 comes after chapter 6. It is still a two mean comparison. You are still comparing two means, but the readings come from the same person, and that has statistical analysis implications, and that's why it's a separate chapter. All right. So let me give you the data set that we are going to be talking about in this class, for this class. So it's on Moodle, of course. So let me access it. Okay. So it is all the class data is always found in the top section. If you didn't know, it's here, data sets. Okay, so open link in new tab. Now, as I think you know, this is an uneditable sheet, because I don't want the data to be messed up. If you go to diets, which I'm going to reproduce, do you see diet A, diet B? This one. I've also reproduced, if you look at your slides, I've reproduced the first few rows of the data. I think 4 rows. I think I did it for you. So I'm going to do this now. I'm going to copy this and I'm going to put it in our class scratchpad. Okay, I'm going to go to our class scratchpad, our class data, so that you can play with the data. Section 11 data. Where is it? Oh, yeah, okay. Okay, let me make a new tab. And so this is diets. Oops. Diets. Okay. Okay, you should be able to access this. So just go to class data scratchpad. You see the diet data has been put there. In your slides, I have reproduced a few of the first. So do you understand this kind of data? Every row represents one person. This is person number 1, person number 2, person number 3, so on. I was thinking of asking you to generate some fake data, but I think this class is beyond that. You know what this diet is. This is how heavy you are after being on 2 weeks of diabetes, and how heavy you are after being on 2 weeks of diabetes. Okay? Do you see, first of all, that there's quite a lot of variation in people's weights? Some people are heavier and some are not so heavy. That is why this design is good. Okay, so the first thing I want you to do in your slides is this. I want you to write down a few statistics. Can you manually just do one? Can you count the difference in weight? I know this is really easy, but just let me do it once. Take this minus this. Compute the difference in weight for this person, all right? What's this minus this? We don't care if it's negative or what, all right? It doesn't matter, right? Just take the diet A weight and subtract the diet B weight, like that. Now, the whole point asking you to do that is I'm going to teach you how to do this on Google Sheets. You need to learn this, okay? So if you go to our Scratchpad, I'll do it here. Here's what you do. And please pay attention because there will be a worksheet later, which I'll ask you to do this on another data set. So just make a new column called diff if you want. Okay, see what I do? Diff. Go to the empty cell here, press equals, See, it's so smart. It's even suggesting what it thinks I want, but I'm going to show you anyway. Equals, click this cell, hit minus, hit this cell. Did you get that? So click the cell, minus another cell, hit enter. It's so suggested autofill. Just accept, say yes. That's what I want. So in other words, it's so smart, it knows that I want to compute the differences for everyone. So you should have successfully learned how to make a column of differences. What can you see? Can you see that some of them are negative and some are positive? Negative means what? A negative sign means someone actually is less heavy after being on diet in diet. I think it's pretty easy to understand. A positive difference means someone was actually heavier after being on diet A than diet. So there's variation. Okay, let me ask you this. If diet A is more effective, should more of the diff readings be negative or positive? Anyone? If diet A is more effective than B, should you have more differences that are negative or more that are positive? If diet A is more effective. Uh, I and effective means lose more weight. Sorry, I didn't define that. Okay, most people get on diets because they want to lose weight. So if I say, what kind of differences should you see if diet A is seemingly more effective than diet B? Should more of the differences be negative or positive? Negative. Because I've chosen to subtract in this direction, A minus B. All right. Let's just give you a feel of the data. Now, if you look at our slides, what do I say? Fill in these values. NDiff, XBAR diff, SDiff. What are these? Notice these are how many differences are there? The number of differences. What's the mean of the differences? What is the standard deviation of the differences? One thing you need to understand is we have moved away from looking at the individual diets, but those have faded away. The focus is now on the differences. That's very key to understand. Okay? So, can we do this? It's not hard. So let's, as usual, let me fill in some words here. How do you find X bar diff? So I'll revise it with you. You go to an empty cell, equals, what's the code for finding the mean of anything in Google Sheets? Average. Good. So you type equals average, then select the cells that you want to average. Make sure you select your differences. Don't select either diet A or B because I told you the emphasis now has moved to differences. All that, okay. And then hit enter. If you see that you had like minus 0.659, this makes sense. On average, the difference in weight in kilograms, by the way, the difference in weight of the people is about just 659 grams, with A losing more weight. That's what that minus 0.659 kilograms. Okay. Anyone want to tell me how do you think I would find S diff? What is the Google Sheets formula, if you like, for finding standard deviation? Anyone remember? 5-letter word. STDEV. Very good. So equals STDEV, parentheses, select the differences again. No more individual data. We don't want that. Okay. So, and while we are down there, anyone care to tell me how many people were in the data set? Be careful. Can you see the number? How many people are in the data set? Be careful. 180, not 181, okay? Because the first row is taken up by the variable names. Very good. So you know what? I'm just going to fill this in. There are 180 people, and they generated 180 differences. Can you now fill in your slides? I found these things for you. And while we are at it, I'm also going to revise how do you plot a histogram for the differences? Differences. I want to see how the differences look like. There's a reason for this. So what did I teach you before? Select the cell name. That's okay. Select the differences all the way. Okay. Insert chart. And I think it's smart enough to do that's it. That's all you need to do. Select the cells that you want to plot a histogram for, insert chart. What do you see? Does it make sense to you? Where's the middle? Well, the middle is somewhere here. It's actually very symmetric. This is hardly skewed at all. Now, this is not important, but I want to show a contrast between the different histograms. This is a histogram of the differences. What if I wanted to plot a histogram of one of the diets? Well, I could. I want to prove a point. So let me select all this data. How do you draw a histogram of the diets for each diet? Well, if you wanted to do a histogram, just insert chart for that one. Do you see that diet A has skewed data? But you will learn we don't care about the skewness of the individual data because that has faded away. We have transformed it to look at differences now. All right, but more on this later. So let's go back to our slides. Write down the values of n diff, x bar diff, and s diff. You should have seen n diff is 180, x bar diff is that minus 0.659 whatever, and s diff was 2 point something. You copy it down. All right. So define mu diff. Now let me tell you this. Do you notice that I have introduced a new symbol today? Mu is not new, but mu diff certainly is new. First of all, why is a mu there? I am still interested in a mean because we collected weight information from people. It's quantitative. I'm still interested in the mean. But can anyone tell me why? Since I'm comparing diet A and diet B, why do you think I am not writing this symbol as mu A minus mu B? Does anyone know why? I am comparing A versus B. I did an A minus B comparison. Why do you think I am not using the chapter 6 mu A minus mu B? Why is there a need to introduce mu diff as a new symbol? One key to success in math is to always be very careful. When the professor introduces a new symbol, there must be a reason. We don't like introducing symbols for no reason. Does anyone know why you think I've introduced a new symbol? Anyone want to try? Why not use mu A minus mu B? It's not a very difficult question. I just want to see if you have any insight into why you think the need is there. Yes.
So because you could put A minus P or B minus A.
That's a good point. The difference doesn't have to be in any direction, but that's a very good point. But it's a little bit different from what the true reason is. But I get your point, yes. We say diff, the direction will be clear in the word definition, but why don't I say mu A minus mu B? Yes.
Because it's not two groups.
Yes. If I use mu A minus mu B, it will be misleading. It's not wrong, it's misleading. It will give people the impression that some people were on diet A and some were on diet B and bring you back to chapter 6. That is why we don't use that. Very good, thank you. That is why. How would you define this? Every time you see a parameter, the first words are long run. Is this a mean? It is a mean. This is a long run mean difference in weight after 2 weeks on diet A versus diet B. Do you notice the words sound exactly the same as mu A minus mu B? It's a difference. It is a difference between diet A and diet B. So to respect the fact that the data are different, the A versus B comparison is coming from the same person, not from two disparate groups. That's why we put the mu diff there. Some books write it as mu D, okay? I think it's a little bit clearer to say DIFF, but you might see mu D, things like that. Mu diff. This is pretty deep, and you'll be surprised. Many people know about chapter 6. But the fraction of people that know about chapter 7, I think is 1% of people who know about chapter 6. Chapter 7 is not well understood, but it is very important. That's why I stress on it. You are comparing mu A and mu B, yes. But we don't want to say mu A minus mu B because that gives the impression that you are in chapter 6 and you're looking at two independent groups, which is not the case. So that's why. So I'm going to ask you, anyone want to guess? The null hypothesis is obviously going to involve the words mu diff. What do you think the null is going to say? The null says that mu diff is anyone after seeing so many null hypotheses up to now. Anyone have any good guesses? What do you think the null says about mu diff? Mu diff is yes. The null always says that status quo is nothing's happening. There is no difference between the diets. Status quo is always easy. No change, nothing. Everything is the same. Historical data is the same. You are proposing two different diets. There's no difference between them on average. So the null again says mu diff is 0. Now, I am choosing a one-sided alternative. It doesn't have to be one-sided. You have the three options. Less than, greater than, not equal to. I'm choosing in this study to go with less than. All right. I want to see if there's evidence that no, A is actually better than B. You do lose more weight on A on average than on B. I'm choosing to test that. So you want to test this? Now, what am I introducing here? I'm giving you the T statistic in this context. First of all, is it surprising to you that it's T? This is involving a mean. So it's T. It's another T. As I told you, they're all called Z, they're all called T, but the level of complexity depends on what situation are you in. Don't forget that nice picture, which I will treasure forever, right? The fairy tale one. Okay? What road are you on? Is this a mean problem? This is a mean problem. So T. Now, this is the shape of the T statistic. I don't want to complicate matters. There's some standard error things. You know that formula changes depending on the situation. Okay, so let me ask you this question. If the null is true, do you think this statistic is going to be small or big? What does the null say? The null says in the long run, there is no difference between the two diets. Therefore, if the null is true, what should happen to this value of t? Should it be small or big? Small. Status quo says there's no difference. If the null were true, if status quo really is true, then your observed mean difference should be small. Therefore, t should be small, which means what? If t is big, then you have evidence against the null. Same logic once again. Is it clear? Same thing. So small is the answer here. If the null were true, this should be small. So this is a theory-based test. So let me ask you, what do you think the validity conditions sound like for this one? Anyone? You need to have at least 20K. But this will really make my spring break very. I'll be happy about all of my spring break. We can give you. You need at least 20 what? Think carefully. What do you think should you say? It is 20. No success failure here. This is a mean problem. You need at least 20. Is it observations or is it something a little bit more? Yes. You need at least 20 differences, which come from 20 people. So maybe that's what you meant by observations. You need at least 20 differences. And what should not be too skewed? What is the thing that if you plotted should not look too skewed? The differences. You get it. That's right. It is the differences that we are excited about. Everything now, you need at least 20 differences, and the distribution of the differences should not be too skewed. Haven't I plotted the distribution of the differences for you on Instagram? It wasn't skewed. See, that's why I did it. We don't care about the individual diets data. That can be as skewed as you want because we have moved away from looking at the individual diets and looking at differences. So all we care about now is the behavior of the differences. How skewed are they? And do you have at least 20 people? Which yields 20 differences. All right. So here's the T statistic. Not that bad compared to the evil ones we saw in chapter 5 and 6. This is really short. X bar diff minus status quo under the null over S diff over square root N diff. If your eyes are really sharp, you will see that this is very similar to the one mean problem that we talked about. So there is a similarity, but I don't want to stress on that. You can learn this as another formula if you like. This is the t-statistic that you use. And so you can go and compute it. So here it is. Where did I get all these numbers from? From the existing statistics that you wrote down in the, how many slides ago, however many slides ago. X bar div is minus 0.659. S div was 2.214. And the number of differences, the number of people in this diet study was 180. And so you have something close to minus 4, you know. So very big. All right. Now, you know this is a t-statistic. T-statistic always has the issue of degree of freedom. Anyone want to try? What do you think is the rule for the degree of freedom? What have we seen so far? Anyone want to propose anything? Yes, very good. It is n diff minus 1. This actually has been reduced to a one mean comparison. That is why you take n diff minus 1. That's why I always tell students statistics class gets easier as the semester goes on, not harder. All the hard work is done. All the references to t-tables and getting p-values and looking at degrees of freedom. Now it's just variations of the same theme. It's not like playing piano, okay? If you play the piano, I'll tell you this. Some composers are so irritating. They will do one passage in a certain key, and then there's a key change. You have to re-practice. You don't. There's not much advantage. Maybe the structure is in your head, but the way a piano is configured is not the most efficient. You cannot, like electronically, you can transpose a piece easily. But when you play them, there are implications. If you have more black keys or more white keys, it's a totally different experience. This is not the case here. What you have learned earlier transfers automatically. Sometimes things are a little bit too similar and can be dangerous. So be very careful. So the reference t distribution is this. Let me show you. Well, in this case, it's 179, which of course doesn't exist. So since it doesn't exist, you have no choice but to round down and where's my t table? Okay, it's here. So 179 clearly doesn't exist. Go to 120 and have a look. Where's 4 of the charts? So the p-value is less than 0.0005. That's what you can say. All right, if you wanted to get the p-value completely. Okay. What do you think a confidence interval for mu diff is going to look like? A confidence interval looks like this. I want to form a confidence interval for mu diff. What would I use in the middle? I hope it is obvious. If I want to say something about the mean difference, I'm going to use the observed mean difference. Simple mean difference. See, you want to make a CI for this, you use this. Again, I'll say this. What else would you use? It's your best guess of what mu diff is. I'm going to use X bar diff, and then the sum multiplier. And then it's an error, which is exactly the same ingredients as the t statistic. The degree of freedom is the same rule. Because you're using a t distribution, it also comes from the t table, and the degree of freedom is n diff minus 1. Same thing. And I have inserted these for you. I'll show you. Okay, why is it 1.98? Okay, these numbers have nothing to explain. We have seen them already a few times today. X bar diff, S diff, N diff. Why is the multiplier 1.98? I hope it's clear, because if you look at our table, which is, where is that gone? Oh yeah. So if you look at 179, if you want to make a 95% confidence interval, you go to column 3, our famous column 3. Do you see a 1.98 here? You should. So 1.98 it is. And so, can you see that the entire confidence interval is negative? What does that tell you? Is there evidence, therefore, that diet A is more effective? See, 0 is not inside. If a confidence interval for a difference is entirely negative or entirely positive, it means that that method is effective. It's not plausible that 0 is a difference. It's entirely negative. You do lose more weight on average on diet A. So to interpret this CI, we are 95% confident that the difference in the long run mean weight after 2 weeks on diet A versus diet B is between this number and that number. You can put the units in if you want, kilograms. Okay, I know some disciplines, if you don't put a unit in, the professor just goes bonkers, okay? I don't care so much because I teach math, but be careful with the units. So it's between minus 0.9857 kilograms and minus 0.3323 kg. Right? We are 95% confident of what? This is mu. The difference in the long run, mean weight, diet A versus diet B. That whole thing is mu. And then now we come to the last slide, which is always kind of easy. When are you ever willing to generalize any results? Generalization is allowed if your initial sample was random. Very good. That's right. And that never changes. You can only generalize conclusions if your initial sample is random. Can you say that one diet causes you to lose more weight than another? Well, you know causation will only be possible if your study is a what? Or is n. Causation is only possible to make as a conclusion if your study happens to be an experiment. What would make this diet thing an experiment? Be very careful. Think about it before you answer. Everyone has to try both diets. You know that experiments need random assignment. There are two diets only that you're going to give. What needs to be random here to make this an assignment? Does anyone know what I'm saying? Yes. Which diet you get first? You see, you're not saying there's 10 diets, I'm going to randomly choose. No, that's not the point. If the order in which you do the diets is randomly assigned, this becomes an experiment. You can make a causation argument. Very good. So, yes, we can say that if this was an experiment, and for it to be an experiment, the order of the diets had to be randomly assigned to the participants. Excellent. Which means there is one thing I want to point out. If you look back at the spreadsheet, I did put A first and then B. I'm sure you saw that. It doesn't mean everyone did A first, okay? That's just for ease of record keeping. Just because column A is first doesn't mean everyone did diet A first. It's just for convenience of, because we'll go nuts. If I put this person has A first, so I'm going to put A first. This person has B, so B. That would be insane. Don't ever do that. For ease of calculation and to keep ourselves sane, we will put one diet as first, but it does not mean everyone did A first. You have to be careful. It doesn't mean everyone did A first. That was random. You flip a coin. Who does A first or who does B first? That's random. Okay? Everyone does both, but which one you do first or second has. See, what I'm trying to say is this. You see, diet A, diet B. It doesn't mean everyone did A first. That's just for computation's sake. Okay. Okay, this is good. So I don't think we will have the time today to discuss this sheet, but I want you to fill it in and make sure you take a picture. We will, after spring break, come back and review this. So finish it manually, take a picture, and then you can go if you're happy with this, okay? Oh, okay, great. And I will, of course, give you the data set for this one. Yes. Hey, you can go, I want to give you all a bit of a break before break. And because you all were good enough to come for class. Okay. So here's the data for this one. Now I know I don't say it in the assignment. Can you make a histogram for the differences here and email it? It's not stated explicitly as a question. Okay, and I found that I need to ask this because sometimes students don't know how to do this thing. So make a histogram for the differences for this data and send it my way by email. All right. So let me give you the data and I'll explain what this data is. So first of all, I will need to create a I will need to create a new sheet here, tab. Okay, this is JJBK. I'll explain. Okay, so JJBK is the data. Here it is. Hmm. You basically do exactly what I showed you previously. Here's the data. Okay, so let me explain. If you read the description, if you read the description in the thing, I'll try to explain. These are people's, every row represents a person. See, every row represents a person. So what you need to do is make your own copy of this. Don't work on this. I want the class to have this clean as well. So you copy this onto your own Google Sheet and do that with your friends. What are these? These are heart rates of people after doing jumping jacks for 30 seconds and pulse rates after doing bicycle kicks for 30 seconds. You get it? Can you see that there's a variety of different levels of fitness in the subjects? There are some insane people here, let me tell you. I'll say insane because it is insane. Can you imagine you did jumping jacks for 30 seconds and your pulse is 70? This person is super fit. This is amazing. This is not me. Okay. My pulse rate is 70 watching TV. Right? Huh. Now, I had a friend who would run these insane 40K marathon things. So I asked him, what is your pulse rate when you're resting or sleeping? Anyone want to guess what it was? That's a good guess. It was lower than that. 29. It was like 2 seconds would pass before your heart beats once. I said, how are you not dead? 29. Well, apparently there are people who can do jumping jacks for 30 seconds and have a pulse rate of 70. That's awesome. I told my friend, you're like a bear hibernating in a cave. You know, bears, their heart rate goes down to like 4 minutes or something when they're hibernating. It's still not understood why they're not dead. Their body goes into severe shutdown. Seriously, four beats a minute. I think I'm right. You can check it out. I think it's four. It's insane. Okay, but anyway, the point is, that's the data set. Okay, so can you analyze this in exactly the way we've done, and try to fill in as much as you can. Like this sheet, take a picture, write your name, give it back to me, then you can go and happy speak with it. Okay. Now, if you have any problems with the Google Sheet part, please raise your hand. I'll help you.